Thanks Evelina for the introduction, and also thanks Maurice for advertising our work on Monday. And okay, today my talk is about the proof of Delfino and Viti conjecture. Okay, this is based on joint work with Maurice Ang and Xinsun here, and also Ge Cai, who is a PhD student in Peking University. Let's briefly record the basic setting on the 2D set percolation. We start from some triangle lattice T here and color each vertex white with probability P and white with probability 1 minus P. Look at this picture, and we consider blue percolation, which means we color independently. Or we can also consider the dual graph and color the face on the hexagonal lattice. And we can vary this probability P, and we see the phase transition at the PC equal 1/2, which means there is no infinite white cluster for this P smaller than 1/2, and there is a unique infinite white cluster for P larger than 1/2. In this lecture, we consider the critical point PC is which is 1/2, and we consider the scaling limit. Okay, now before introduce our result, we first mention some significant developments in the 2D critical site percolation. The first one is by Smirnov. He proved the Cardi crossing formula. And the citing is you consider this triangle and the mark point ABC and the mark point D here, and the length of this is square root 3x, and you put the critical percolation and consider the scaling limit. And you can ask what is the probability that there is a percolation cluster crossing from the edge CD to the edge AB, and the exact probability is just x. And there is another thing development directly from the continuum citing is the construction of the scaling limit of site percolation, which is given by which is called the SLE and CLE by Smirnov and Sheffield. And later, Tamir Newman give the existence and also the construction of the full scaling limit, the CLE6. In our work, we also use the results by Christoph Peterstram, the scaling limit of conformal covariance of the pivotal site and the cluster, and also the derivation. Okay, now we to introduce our work, we start from the one-arm exponent. We consider the set percolation on the triangle lattice with delta t with my size is delta. And we define the event like pi delta is the probability that on this triangle lattice, what is the probability you start from 0 and to reach the boundary of the unit disk. And the probability is behaves like some delta with some exponent with beta plus 0.1. And later the Lohr-Schramm-Wiener proved that the exponent is like 5 divided 48. Now we consider if we have endpoint on the full plane and xi delta is their approximation on the triangle lattice, and we define the probability that this endpoint belongs to the same open cluster. Record the P here is PC equal 1/2, and then we consider the limit that we let the lattice size, the mass size go to 0, and we somehow renormalize this quantity by this one-arm probability. This classification, this one-arm probability. And this one, by several work initiated by Osman, and later by Gaban Peterstram, and also by Kamir, proved this quantity exist and satisfy some conformal covariance. Especially for the 2-point and the 3-point, if we let this x, y, x2, they move them far away from each other, it decays like this x1 minus x2 with this particular rate. Now, from this formula of 3-point P3 and 2-point P2, we can get we can define something called the percolation connectivity constant R, which is the ratio of the P3 divided the square root of the product of 3P2. In this particular combination, we see all these xi dependence disappear. Somehow we basically left with this constant C2 divided C2 with the power 3 divided 2. Okay. And the C2, C3, they individually they depend on the somehow the lattice normalization, but the ratio doesn't. Okay, now I will talk about what is the Delfino and Viti conjecture. This conjecture actually inspired by the Chim and Mojikov on their work on the integrable field theory. Mojikov developed some tools on the study the near critical perturbation of the conformal field theory. For example, if you consider the spin perturbation, this theory is somehow integrable. And then later, the Delfino and Viti, based on the result of the Chim Mojikov and also by some 2D conformal field symmetry, they give a conjecture formula of this this R percolation. R percolation is defined here as the percolation connectivity constant. And also do some Monte Carlo simulation, and they got this result like 1.022. Our main result our main result is we explicitly compute this R using this definition here. And this result is given by the imaginary DOZZ formula with the insertion is given by this one. This one I label this like in the sense of in the sense a formula as a class table, but here m and n will be some rational number. And if you have this explicit formula, you can find that it's actually coincide with your numerical things. And not only for the percolation, physics also have some prediction on the FK cluster model. Recall the definition of FK cluster model is given by some additional reweighting, like the number of the cluster. And the critical point is PC equal square root Q divided 1 plus square root Q. And the conjecture is the scaling limit of all the interface between the FK cluster and the dual cluster converted to the CLE kappa prime with the Q and the kappa prime related to this one here, kappa prime larger than 4. And in the same paper, Delfino and Viti also give a conjecture of FK connectivity constant, which is also the ratio of the 3-point function in the same cluster and divided the square root of the product of 2-point function. And they guess the conjecture is also given by the imaginary DOZZ formula. For the spin model, like the Eisen model, they also give some conjecture, but actually in the Eisen case, it's still given by the imaginary DOZZ formula, but the physics have no explanation of this result. Okay, so what is the imaginary DOZZ formula? In the last talk by Morris, he already showed the formula is given by the double gamma function and with some renormalization given by this one. It's a super complicated formula. And the normalization is guaranteed that if you put one insertion is 0 and the 2 other things are same, it give you 1. Like you can somehow somehow compute this by meet this condition by fix this A here. at the end of the last talk, you can ask a question: what's the relation of the real DOZZ formula and the imaginary DOZZ formula? Actually, in the original work by Damlogic, which he invited this imaginary DOZZ formula from some string theory perspective, he already understands some KPZ fixture of this, like the product of real DOZZ formula after some renormalization times the imaginary DOZZ formula is actually 1. The spirit of this is similar to the the spirit of this is similar like the KPZ type things. For example, in the KPZ sense, the matter field and the background geometry, the Liouville field, the sample charge, the summation is 26. Also, the conformal weight of the matter field and also the Liouville things, the summation is 2. So this is like the 3-point generalization of the KPZ formula. Okay. Here I mentioned I will mention the imaginary DOZZ formula. Not only appear in our setting like the statistical loop model or the CLE things, but it also appear in many other places. The original paper by Damlogic, the motivation of he invite this imaginary DOZZ formula. Actually, he want to find a generalization for all the diagonal minimal model. For example, the Eisen model, you can compute the Eisen model, the 3-point function divided some 2-point function. And we want to find a generalization of this thing. That is, we call it the imaginary DOZZ formula. And later, there are several recent works. The first one I want to mention is the Colin, Antti, and Hemi's work on the competitive imaginary Liouville theory. And they say under the neutrality condition, they constructed this theory, and the imaginary DOZZ formula actually coincide with their electrical 3-point function. And more recently, the Schwab Chatterjee, he under the neutrality condition holds, which means the weight of the 3 insertions satisfy some linear constraint. He found he constructed something called the time-like Liouville theory. Which is different from this one. And the imaginary DOZZ formula also coincide with the 3-point function of the time-like Liouville theory. And during last break, I also know the work appeared yesterday that you see Tati, Koman, Hemi, and Ross and Hara, they give a construction of time-like Liouville theory. And in this case, they remove the assumption of neutrality condition, but they assume some nice properties of the imaginary GMC. And they also did some numerical simulation, and actually the 3-point function coincides with the imaginary DOZZ. Also, here is some background on the CFT thing. The CFT is 2D CFT is motivated like by the random surface, like the LQG stuff and the 2D lattice model. And there are some algebraic citing for this algebraic story for the CFT. And the CFT is recently becomes more and more important and interact lots of error in the in math, like the representation and the geometry, also probability. Here I just show the one result, like the Eisen. If you consider the critical Eisen model and compute the spin correlation, this is sigma is spin and epsilon is energy. You consider this is 3-point function. It's the 1 or 2 is actually coincide with the imaginary DOZZ. As I mentioned, the imaginary DOZZ is somehow a generalization of the structure constant of minimal model. Okay, now we get back to our story. So we see that not only for the percolation and also for the FK model, the three-point function, the connectivity constants, they are both given by the imaginary DOZZ. Now we could imagine some universality. So we know all this custom model, the scaling limit is always given by the so-called conformal loop ensembles. The conformal loop ensemble was constructed by Sheffield, and also there is a loop super construction by the Sheffield winner for kappa smaller than 4, and the Sheffield construction is using the exploration of branch tree and can be worked for the until 8. And there is also a full plan version of the CLE kappa. Basically, you just first define the CLE on the some bounded domain and prove there can somehow there is some coupling. And the CLE actually describe a lot of interesting statistical models like the Eisen and the side percolation. These are rigorously proved by Camille Newman and Benoit Honnet. And also there is a conjecture, the CLE kappa is conjectured to be describe the limit of ON loop model. Another model, not FK, but it also describe the scaling limit of FK cluster model. Here, this picture I borrowed from the Morris side. Like here, you imagine some ice, and the pink one is the pass spin, and this is a minor spin. And you look at all in the interface and take scaling limit, you get this kind of picture. Also, there are countable many, but infinite loops here. Okay. Now we describe something called a CLE cluster. Basically, they are just some CLE carpet and gasket, but now we want to adapt this to the sphere setting. The CLE carpet and gasket is formed by points that are not surrounded by any loops on CLE. For example, this point here are not surrounded by any other loops on CLE, from CLE. On the sphere, we define something called the CLE cluster. Basically, we want to, because we want to understand all the clusters. We want to count all the clusters. So we also need to count the cluster here, which are surrounded by these loops here. We also want to count not only this CLE carpet, but also want to consider this kind of clusters. There are countable many on the sphere. There are, because of some nesting structure, there are countable many CLE clusters on the sphere, and each of CLE cluster is surrounded by countable many CLE loops. For example, here, this cluster is surrounded by this loop, also this loop, and also this loop. Somehow we want to remove some redundancy. How can we do this? We first sample. Maybe we just fix an infinite point on the full plan, on the sphere. We fix the infinite point and use the counting measure to sample a CLE loop and look at the CLE gasket inscribed in this loop. Like this, we fix the infinite point here, and if we want to describe this cluster, we just look at this loop and consider the inscribed CLE carpet. Use some conformal invariance property of the CLE gasket. Okay. Here there are some difficulties. Even we remove this kind of redundancy, the counting of CLE loop is still an infinite measure. So this infinite measure is actually interesting and starting out in the last 20 years maybe. Yeah, 20 years. It's called the Malevin conservative so-called restriction measure. Basically, it's defined by something called conformal restriction, which was introduced by Hausdorff talk on Tuesday. You can define this measure by using some restriction property and add some additional loop measure. And this measure is recently proved to be unique up to constant by Guillaume Barres and Anton Diego. And recently there is another proof directly based on the loop super construction for the restricted strange, like the kappa other than 8/3. This proof for Barres and Diego's work is for all kappa. the existence of SLE kappa loop is non-trivial and is constructed by Baojun. And this is the infinite positive measure on the support on the single Jordan loop. For kappa smaller than 4 is the Jordan loop. For kappa larger than 4, there are some touching point. So here, as I mentioned here, the SL loop is somehow defined like up to a constant. But what is important for our work is we indeed need to fix this constant. We consider the SL kappa loop separate from separate 0 and infinity because some scale invariance we can somehow decompose the SL loop as this SL loop. I mean separate means here I use SL kappa separate means separate 0 from infinity. I can decompose this to the big measure and times something called a shape measure, which is the probability measure. Basically, I want to for arbitrary Jordan loop, I can somehow ask is it touch the unit disk from interior, and this one is called the shape measure. And the SL kappa loop measure is somehow this one and times the big measure. Then our result, we found that the counting a CLE kappa loop, there are infinite many loops on the sphere, and we counting a CLE kappa loop is actually a SLE kappa loop measure. What's more, we can exactly fix this constant with respect to this phase measure. This phase measure is L kappa, which is a probability measure called the shape measure, and also the big measure. We can exactly fix this constant.
By fix, you mean compute?
Yeah, compute.
This is something.
This is something non-trivial. It's compute. How to fix this? How to compute this constant? Basically, we use the counting measure. We only need to understand, for example, on the unit, I say on the unit disk, we want to somehow measure how many loops which are disjoint with some fixed some C here, and disjoint with this small board. And we, if we don't fix, we just consider all the CLE loop surround the origin, then there are infinite many loops. But if we fix this C here, the small board here, as the loop doesn't disjoint, is disjoint, the loop disjoint with this small board, there are only finite many. Now we count the number of the loop, disjoint. Divided C, and we take the limit of C. This one will go to give you something like this one. Given by the conformal radius. This is basically based on the Markovian properties of the CLE. Something like this.
So what is DT?
DT is the big measure.
Yeah. So what does it mean? The T.
T is basically means if we consider CLE is the conformal radius of the CLE loop is distributed as the big measure.
So it's some sort of a conformal radius.
Yeah. The log of conformal radius is the big measure. Maybe we choose this exponential method C here. Maybe it's more convenient to map the sphere to some stripe and look at this unit disk is mapped to the here some vertical line here, and these are some loop here, and count we fix some range like here we fix some interval I and count the number of the loop in this interval I, and this is just captured by the log of the conformal radius.
The calculation, the conformal radius still depends also on color.
Yeah. The conformal radius, the formula of conformal radius is found by the Schramm, Sheffield, Wilson. It depends on kappa. It's constant. in our work, this is constantly important. We will see why this constantly is important later. Then the next job is, no, I already described how to choose a cluster. Choose a cluster, I first use the counting measure sample loop and consider the inscribed carpet. The next job is how to describe the points in the same cluster. To describe this, actually we need to consider some nature measure on the CRE carpet. This is some analog of the Minkowski content of CRE carpet or gasket, but the existence of Minkowski content is not known yet. So actually, we to construct this nature measure, we use the LQG method. This is constructed by Neil Sheffield Winner, also Neil Shun. Okay, how to construct this? As Morris talk mentioned that all the outermost loop can be somehow the quantum length of the outermost loop can be encoded by some Liouville process. And to define the nature measure, we first define something called the quantum nature measure. The quantum nature measure is basically given by here you fix open set U and you consider the number of outermost loop in this CRE with the quantum length larger than epsilon. We denote this by this n epsilon h gamma. H is the field and gamma is the CRE. And using the exact Liouville process description, one can prove that if we choose a beta with this number and consider this renormalization, take the limit go to 0, the limit exists. And the quantum total mass of this one is just given by the stopping time of the Liouville process. This can be checked directly. You see the quantum nature measure is basically given by the information of the quantum length information of the outermost loop. And all this outermost loop quantum length is encoded by some Liouville process. And to define the nature measure, we just average all the randomness of the field. Then we get some PPZ type relation, like this quantum nature measure given by the field fluctuation with this particular exponent beta and times something called a nature measure. Then use nature measure. We can use nature measure to sample some point and define the green function to as a definition of the several point in the same CRE cluster. So we move the sighting from the percolation things to the directly to the in the continuum. We consider CLE, and on the CLE we first sample a loop from counting measure and consider the inscribed carpet and use a quantum nature use the nature measure defined in the last side and define the green function. And if we consider the ratio of the 3-point green function with the 2-point green function, our theorem gives this constant is actually the imaginary DOZZ. For the percolation case, actually we can prove the thing in the discrete side percolation indeed convert to the CLE nature measure definition, which is based on some previous work by Gaban, Peter Schramm, Kamir, Kojin Case, and also Delfino and Viti. In the percolation case, we can indeed prove the limit convert to the R percolation with in the discrete setting and convert to this R cluster with kappa equal 6. Okay. The proof strategy is basically similar to Morris' talk about the computer, the 3-point function of the 3-point function of a conformal radius. But here we have some additional difficulties is to compute some Liouville process quantities, like some joint law, some stopping time, and also some jump process and weighted by the quantum area. And this one we somehow use some we show we have some knowledge from physics literature about the string equation and the matrix model, and we show this one can be somehow encoded by some solution of Bessel function, a solution of some hypergeometric function. Yeah, this is how we prove this kind of result. And then use some KPJ formula between the DOZZ formula and the imagined DOZZ formula, we can get our result. Okay, there are some other results on the about some geometric 3-point functions. The first, the second one I want to mention is like the 3-point on the same loop. If you have some SLE loop which was chosen by the counting measure from CLE loop, then we can compute the probability somehow. The 3-point in the same loop. In this case, this is given by something called omega function, which is not imagined DOZZ. When I check with this exponent, imagined DOZZ somehow go up. This omega function is also written by the double gamma function, but it's much more complicated. You see there are some absolute value here which somehow breaks the shift equation. This formula can be somehow thought as a generalized imagined DOZZ formula from the diagonal field to the non-diagonal field. This formula was introduced by Ribble and Jacobson. And this also related to the Kappa imaginary Liouville, like or the Coulomb guys, some mixed electric magnetic operator, which is not a diagonal operator. And also recently, this was shown to be related to the E series minimal model, structure constant. Finally, I want to mention another result. Before we consider something, the percolation cluster or the FK cluster, the final result is we want to consider the Q-pulse spin model. For example, in the like 3-pulse model, you have a different color. Like what you can color this, you can put the spin with some label 1, 2, 3, and you want to consider the spin cluster. We can define the similar connectivity constant which given by the several point in the spin cluster. For Q equal 2, which is the Eisen case, this is known to be coincide with the imagined DOZZ. But this is not true for other Q. The explicit formula is missing even in the physics literature. Our result is this connectivity actually is very similar to the imagined DOZZ formula, but differ by a constant dependent on Q. Q and the kappa related as this Q is the QFK cluster. And this constant actually has some very nice geometric meaning. It's given by the some conformal radius, some ratio of conformal radius, and we compute explicitly this ratio. And our result somehow we use this explicit formula, and this coincides with the physics numerical result. Apparently, mention some future perspective, like here we show several geometric 3-point functions, but actually you have many different kind of 3-point geometric 3-point functions. How can we compute this 3-point function, like 3-point function on the sphere, and also some boundary correlation functions? To compute the boundary correlation function, we also need to understand the boundary condition, like the free wire boundary condition, and some other boundary conditions. And another very hard question is how to compute the 4-point connectivity, say the 4-point in the same percolation cluster, and how to prove the conformal bootstrap in the sense of Liouville case. And another very interesting question I think is asked many times during last few years is what is the exact relation of the conformal loop ensemble and the Coulomb gas. For example, can you use our result to get some explicit formula like the imaginary GMC moment or some Laplace transform of the imaginary GMC? Finally, I want to mention there could be some potential relation of between the CLE and the minimum model. For example, in our recent work with Hausdorff and Zhang here, we compute something called mixing rate exponent, known as the FK energy exponent, using the CLE execution method. Okay, I will stop my talk here. Thank you.